Good morning, dear students. Uh, Last session, we have started talking about kani's method, which is displacement method. Uh, Another, distribution method after the moment distribution method. So, also known as rotation contribution method. So, finally, it was discussed in the last session that Uh, the final end moment to calculate according to kani's method is fixed end moment plus 2 times near end rotation contribution and plus far end rotation contribution. This is what we need to use the formula to calculate final end moments in a structure. So, where we have already discussed in the previous semester how to calculate fixed end moments. Now it is to discuss about how to calculate this rotation contribution. So, if you know this, then you are able to find final end moments. So, let us see what is meant by rotation contribution and how you calculate it. So, take a structure, plane frame where there are a number of beams and columns there. Okay, so imagine a structure like this. So I just concentrate on this joint A. Okay, so where there are four members meeting joint A, AB, AC, AD, AE. Okay, so now if you apply that formula, what is MAB? Okay, which is fixed end moment MFAB plus 2 times M dash AB plus M dash BA, which means what? Fixed end moment at A due to loads. So we are writing for member EAB, this one. 2 times near end rotation contribution plus far end rotation contribution. Similarly for AC, EAD, EAE for all the members AC, AD, and AE. Okay, right. So once you write that, let me erase this one. So we need to draw some deformed shapes like that's why, right? So we have written all end moments at A. If you see, this is moment at A from AB, moment at A from AC member, moment at A from member AD, moment at A from member AE. These are all the end moments. Now, total end moment at A, because there are four members, you'll have four values. So I'm just combining all of them. So sigma M, actually MAB plus MAC plus MAD plus MAE. So we are replacing that by a sigma symbol AI, where I is B, C, D, E. Means what? If you expand this one, it's like MAB, substitute I is equal to B first, then C, okay, likewise, then D, then E. What you get? AB plus AC plus AD plus AE. So this, all these four values are combined in this single term. Okay. Similarly, all this sum of fixed end moments at A from all four members and 2 times sum of all near end rotation contributions plus sum of all far end rotation contributions. Means what? BA plus CA plus DA plus EA M dash values. So this is the instead of writing four equations, I have just converted it to a single equation. Right. Coming to next. So from joint equilibrium, the total moment at A should be zero. Okay, the same equation we have been using even from moment distribution or from slope deflection. So the total moment at A shall be zero. Okay, so that is sigma MA should be zero. So equate that equation to zero. So our target is to find the equation for rotation contribution, which means m dash value. So separate that m dash term, this term, send other terms to the far end, the right hand side. So this will go to right hand side and this will go to right hand side. So 2 times sigma m dash ai is equal to this if that goes to right hand side, it will become minus sigma m f a I. Okay, and this has come to right hand side. This also has come to right hand sigma m dash ia. So 2 is here. So if that also goes to the right hand side, it will become 1 by 2. Okay, the 2 times it is 2 times actually. So 2 goes to right hand side. So that will become 1 by 2. So I have just written straight away 1 by 2 times. So this is rotation contribution of near end. Okay, right. What next? Let this be 1. Okay, right. From figure 3, what is figure 3 earlier here? From figure 3, what is 2 times m dash AB value? It is like stiffness value. Okay, so 4 EI by L from stiffness. This is rotational stiffness of the member. M by theta is stiffness. So M is equal to stiffness into theta, K into theta. Okay. So 4 EI by L into theta A. So let's substitute that one. So 2 times M dash AB is equal to 4 EI theta A by L. So what I'm writing this one is stiffness of AB, KAB. Okay. So K value, we have been using K value even moment distribution method also. What is K if the far end is fixed? 4EI by L. So KAB into theta A. Okay. So what you can write for M dash AB? KAB divided by 2 into theta A. This is for member AB only. From figure 3, right? Similarly, you have AC, AD, AE. So if I can combine all those, I can write KAC by 2 theta A. Theta A is common. Okay, EAE. So I am writing single term for that. Sigma K AB EAC EAD AE. Likewise, because theta A is common, so you can take it common from all the terms. So this is a single term equation for near end rotation contributions. Okay, so the angle of rotation is same for all the members in a joint. So if theta A value, if A rotates by an amount of theta A, okay, this if it is clockwise rotation, all the members will rotate by same amount like this. Okay, like this. this. So joint A rotated by theta A. So if even if it is AB or AC or AD, AE, theta is same for all the members because it is joint rotation. If the joint is rotated by some 5 degrees, member AB, A rotated by 5 degrees. Similarly, member AC, A rotated by 5 degrees. Likewise, you have to understand. Okay, right. What next? Now, so you have from M dash AB divided by KAB is equal to theta A by 2. Okay, so take this and these two, write it like this: M dash AB divided by KAB is equal to theta A by 2. Similarly, sigma M dash AI is divided by this is equal to theta A by 2. So now what I can write: M dash AB by KAB is equal to sigma M dash AI by sigma KAI. That is written here because theta A by 2 is common here and here. Okay, theta A by 2 is common in these two, right? So that's how it is. So M dash AB by KAB divided by KAB. Okay, so I'll just mention it here. M dash AB divided by KAB is equal to what you can write: sigma M dash AI divided by sigma KAI, which is equal to theta A by 2. That is not required. Okay, this is the equation. Now just rearrange this one like M dash divided by sigma M dash AI. This just rearrange. So this comes sigma M dash AI comes to denominator here. KAB goes to numerator. Okay, so this is what it is. So M dash AB by sigma M dash AI is equal to KAB by sigma KAI. Okay, so what is M dash AB? KAB by sigma KAI into sigma M dash AI. Okay, so why we have written like this? Because we want this value to know how you calculate rotation contribution. So again, M dash AB is equal to, expand this one. What is sigma M dash AI? Okay. So sigma M dash AI means, again, from the earlier equations. This is what you see. From equation 1. What is sigma M dash AI? Minus 1 by 2. Already KAB by sigma KAI is there. Minus 1 by 2. This into sigma fixed end moments, sum of all fixed end moments at A, and sum of all foreign rotation contributions. Okay, so what is this term called in this derivation? This is called rotation factor, just like your distribution factor in moment distribution method, where what is distribution factor? It is K by sigma K, right? K divided by sigma K. What is rotation factor now? Minus 1 by 2 times K by sigma K. Okay, so total rotation factor at a joint shall be 0.5. Okay, because if you have say two members at a joint like this, So if this is joint B, for example, so BA rotation factor, if it is minus 0.2, BC rotation factor shall be minus 0.3. Total should be minus 0.5. Just like total distribution factor shall be 1. So total shall be 1 where distribution factor, right? So in case of rotation factor, the total shall be minus 0.5. Okay. So this is what is required for the method. You need rotation factor. Okay, you need rotation factor multiplied by sum of all fixed end moments. So if you want rotation contribution of particular end A in a member AB, okay, so you have to multiply rotation factor with sum of all fixed end moments at that end A and also sum of all far end contributions. Okay, so if you see the diagram, if you want the rotation contribution for this member at A, what you need to do, rotation factor multiplied by sum of all these fixed end moments of that NDA plus this one, sum of all far end rotation contributions. From B, what is rotation contribution? From C, D, E, okay, all far end rotation contributions shall be added to this, okay. So these two terms, okay, shall be added. So that will give you rotation contribution at A in member AB. Okay. Similarly for all other members. For member AC, what is rotation contribution at A? If you want, use the same formula, right? So this is how we are able to find required terms to calculate end moment. Okay. So in this rotation contribution method, if you want final end moment, you need fixed end moment and rotation contributions must be calculated, whether it is near end or far end, whatever it is. First, you need to have a formula for calculating rotation contribution. So that is being derived in this session. Okay. So the procedure to derive rotation contributions, you have to practice it very well. So it is nothing but rotation contribution of particular end is equal to rotation factor, which is nothing but minus 1 by 2 k times sigma k of that particular member divided by joint stiffness multiplied by sum of all fixed end moments of that particular near end and sum of all far end rotation contributions. Okay, so that is to be calculated to substitute in final end moment equation. Okay, right. Next session we will discuss about the procedure. Then we'll go for one example. Right. So this is the brief, you know, recall of what happened in this particular session. So, in this session, we have concentrated on two things. What is meant by rotation factor, what is its value, and what should be total rotation factor value at a joint. These three things, plus how to calculate rotation contribution, what is the formula, how to develop that formula. Okay, so rotation contribution formula, rotation factor formula, what is the maximum value of rotation factor at a joint, right? All this is being discussed. Okay, right. We'll go for the next session in the with the procedure to solve a problem. Okay, thank you.